As you're writing that down, I hinted earlier that there's actually a sort of relationship between the algebraic sort of calculation of a dot product, so like the number that you're getting, I suppose, and a visual sense of what's going on. It's because we saw that with our dot product, we could actually get positive and negative numbers. And there's actually a good reason why. So let's just have a look really quickly at an example. I'm just trying to get this out of the way so you can actually see what I want to put up. So let's look at this guy. So here I've got an example where it's calculating the dot product and it's giving me a number out there. Right now it's positive, which is fine, yeah? So I've got two vectors here. I can change the length of the vectors, and what you notice is I change the length, it, I guess, increases the dot product. And then let's have a think about, what if I change the angles? Give me an angle I could do.
89.75.
That's very specific. I don't know if I can quite get to 89.75. I can get to 80. I think that's the closest I can get. Oh, now I got obtuse. But just tell me any observations you sort of notice as we're going around. Yeah.
Negative?
Yeah, where's the negative?
It's like obtuse.
Obtuse, okay, so it's interesting. When it seems obtuse, it looks like it's going to be negative. I could change this one as well if I want, and that still stays the same, right? Anything else that you'll notice? I'll just keep going around.
As it becomes bigger obtuse, it gets bigger negative.
Yeah, bigger obtuse, bigger negative. Cool, cool, cool.
This right angle zero.
Yes, that's a very important fact. Right angle is 0. Okay. Basically, we're trying to think about, okay, there is an algebraic interpretation of this where we just do the calculation, right? It's also a visual understanding of this in the sense that we've seen that there's actually a very close relationship between the angles of the vectors and the dot product which is produced, which actually opens up a new way to access the dot product. And it's not just looking at getting a number at the end. It's actually looking at the angle between two vectors. So essentially what's going on is if you take two vectors and you look at the angle between, that looks like a right angle, so I'm going to do that a bit more ambiguously, right? And you look at the angles between them, we say that there's a relationship between the two vectors in relation to their scalar or dot product, right? And the relationship is this. Remember, we wanted this criteria. We wanted that basically if A and B were obtuse, right? What happens to the dot product? The dot product was negative, yep. And if A and B were acute, then it was positive. And if A and B are 9 degrees, yeah, then it was 0. This is the most important fact that's going to help us think about what is the relationship here, right? When they're 90 degrees, think about when two things are 90 degrees, why might it be 0? Go back to things that look at angles, right? And one thing closely related to angles is trigonometry, right? Is there a situation when we have 90 degrees and that gives us a result of 0? That's what I'm trying to think about, right? That's my question. So is there a situation when we have 90 degrees and that gives us a 0? That's sort of the question I have. So what sort of trig situations do we have? Like when we use trig, when we're trying to find angles, what kind of tools do we have available to us when we're trying to find angles related to trig? Sine, cos, tan, right? So is any of those situations going to lead us to 0 when we have 90 degrees is my question. Won't be tan, because if you remember, tan of 90 degrees is actually undefined. Yeah, so cos 90 is 0. That gives us a big clue. And actually, if you look at this situation here, what does this kind of resemble? Yeah, it's kind of like a triangle, isn't it, right? So if you wanted the vector, for example, this one, That's the vector b minus a. And actually the proof for this, so I won't do it for you now, but the proof for this involves using the cos rule, right? Cosine rule. And because basically what you're doing is you're finding a relationship between the angle between the two vectors and the vectors themselves as well, right? And you'd have to use a combination of these properties here. But the rule is this basically, right? Because we're noticing these patterns here. And so essentially we've got, okay, the dot product of my two vectors can be written another way. It can be written like this. It can be written as, okay, if I want to find the dot product, I can take, you know, what do these absolute values mean again? They are the, making them positive, or the magnitude to distance. It does work for a number. It doesn't really work for vectors though, because you can't just make them positive, right? So again, different things mean different things in different contexts. So here we've got the two magnitudes multiplied together, and we've got cos of the angle between them. What that means is now we can sort of find and answer questions related to the angles between two vectors, right? For example, let's say we've got this example. Something like this here. They give you all the tools that you need, and before we wouldn't really be able to find them, find the dot product, because we only knew how to do it from the coordinates. You couldn't actually. I was gonna say you could probably try and find them, but you can't, because all you get is the magnitudes and the angles between them, right? So basically for this one, what we have to rely on is this new definition that we've got, right? We have the individual magnitudes, which is great, and we actually have the angle between them, which is good. So if we want to find u dot v, then all we have to do is we say, okay, well, we've got u dot v is equal to my two magnitudes multiplied together, so 7 times 5 times cos of that angle, cos 74 degrees, right? And again, remember the dot product, the scalar product, it's just a number at the end of the day, right? It's just going to be a number. So maybe a nice number, maybe a whole number, or maybe some decimals as well. But go ahead and find that for me. Did you get an answer for this one? Okay. What'd you get? 9.65. Yeah? Is that it? Or is there decimals? That's it? Oh.
Oh, no, it was decimals.
Oh, there was? Is that rounded already? To what? 2 dp? Yeah. Okay, perfect. Alright, cool. These ones here, dot products, hopefully we're pretty good at these now. Lily, do you want to do, are you doing the first one for me?
Yeah.
What did you get?
I got 3.0.
Yeah, so 4 times 12. Yeah, 3 times negative 5. And what was that, sorry? 33. Yeah, easy. Cool. Angle between the vectors. So we already know actually, if it's a positive number, what kind of angle should it be? Acute, right. So we actually have this little guy here. That's all good. So that's sort of some significance behind the number that we're producing. How can we actually find the angle though? Yeah, so basically we can use it, we're interested only in this component, right? So we can essentially just rearrange them. So we go ahead and we say, okay, the dot product, conveniently, and this is what they'll tend to do, they'll tend to give you the first part to find the dot product. So we know that's 33, and we could write out what we've got here. So we can say u dot v is equal to the magnitude of u times the magnitude of v multiplied by cos theta. Do we have the magnitude of u and v, by the way? Yeah, so just be careful. Remember, there's a difference between like this and this, right? This is the dot product, this is the magnitude. And what's the magnitude? Well, it's 4 squared plus 3 squared, or 4 squared plus 3 squared.
So use 5.
Yep. That's a Pythagorean triple, actually. That's quite nice.
And the other one will be 13.
Yeah, so they've chosen some nice whole numbers for you. Easy. So then you just put them in. So 33 equals to magnitude of u, that's 5, times the magnitude of V, which is 13, cos theta, and how are we going to find cos theta? That's right, so just rearrange, so cos theta equals to 33 on, was it 65? And then take the inverse cos of that. To find that out for me, okay?
39, wait, 59.
Yeah.
Could you read out like the angle symbols again?
Minutes. Yeah.
59 degrees and 29.
29. Yep, 29 minutes to the nearest min. That's rounded, I guess. Just to, yeah, seconds, yeah. We're very creative. Why not hours though, right? Just to sort of clarify, when we're finding the angle between two vectors, notice our measure here that comes up. You might notice that, okay, we have the acute and obtuse ones. What other types of angles do we have, apart from the right? Oh, actually, just to clarify, by the way, we didn't do any more of those, but we'll talk about this later. This is why when we have 90 degrees, cos of 90 is 0, so that's why that one's always going to be 90 degrees when they're perpendicular. But we're missing one type of angle, actually. Yeah? What are the, do you remember what it's called? Yeah? Oh, you don't know? Begins with, sorry? Begins with
Are we
R.
talking about the flat one?
No, well, we did.
We're talking about the backwards.
The backwards one, yeah. We do have a flat one. Flat one's this one.
Yeah.
There you go. There's a horizontal one for you. Yeah, it begins with R. Reflex, if that's familiar. Yeah. Sorry. Yeah, geometry. Sorry.
Back in the 6th that I learned.
Yeah, year 6 geometry. No one cares about that. But basically, the idea is, when we're looking at this one here, there is essentially going to be two angles all times between two vectors. You can find the acute or obtuse angle, or you can find the reflex angle, but the dot product basically assumes the non-reflex angle. And that's how we define the angle between two vectors. It's the non-reflex angle there. So just make a note of that. The angle between them is the non-reflex one, okay? And that's the last thing you need to know, all right? And that's the scalar dot product there.